Hello, class. So throughout the first period of this week, we are going to go over alcohols and discuss the addition reactions related to alcohols. Now for the resources for this week, you will use your textbook pages 807 to 809. You will use the PowerPoint slides, and for distance learning students, you have the recorded lessons. You will have a video related to the concept, an MS Teams assignment for the chemistry, a SAT assignment, and for FTF you will be having a forms assignment. For this week's guide, what I need you to do is head to Files on MS Teams, download week 10, read the textbook page 807 to 809, go over the PowerPoint slides prior to attending the period. Points 2 and 3 are mainly for for FTF. For DL, you are going to find it in Files in Teams. For FTF, you're going to find it in the portal. Also, for DL, watch the recorded lessons and then attend the live session. Ask questions to make sure you get the concept and solve the MS Teams assignment. For this week's objectives, I need you to describe how addition reactions are used in organic chemistry, to apply the understanding of the three types of addition reactions, and to compare the main difference between the three types of addition reactions. When it comes to the keywords for this week, addition reaction, hydration reaction, halogenation, and hydrogenation. These are the three types of addition reactions. To start with, I'm going to be giving you a 1-minute timer to actually refresh your memory on naming alcohols. Let's start the timer. So time is running. Pay attention. Try to refresh your memory on naming these alcohols. Time is up. I hope we got it correctly. Let's check it together. First of all, locate the longest chain and number closer to our branch, our substituent, that is an alcohol, not a methyl group. So 1, 2, 3, 4, 5. How do we name it? What we need to do is locate both substituents on which carbons, 2 and 3. So I have 2. What does 5 mean? 5 pentane. And when we convert to alcohols, we remove the E, add OL. So it's pentanol. Where is the location of this alcohol? Carbon number 2. And then what is my other substituent? 1 carbon, so meth. And we name it like an alkyl group. Remember the location, carbon number 3. So 3 methyl 2 phenyl. For the second example, notice that we have 2 alcohols. So immediately, diol. How many carbons? 1, 2, 3, 4. 4 carbons, butane, diol. What is the location though? Carbons 2 and 3. I hope our memory was okay now when naming alcohols, and we've got a fresh start. Now, what I need you to do is I'm going to give you 1 minute. I need you to take a look at these two reactions and try to describe what is going on exactly. Okay, unfortunately there's something wrong with the timer. Okay, so the timer started. Please try to analyze the reactions. You can see some things that are very clear. Observe the bonds, substituents, what changed, what happened. Okay, so time is up. Let's see. We can clearly see one very important thing. We have a double bond, now we have a single bond. So the double bond was reduced to a single bond. We can, we can also notice that the first reaction, the product was alcohol. Okay, so in the first reaction, we can notice that the product was alcohol. And in the second reaction, it's a halogen, or sorry, a halocarbon. So we can easily say that these reactions add specific things to get a desired product. Keep the reactions in mind so we can actually see why we have such reactions. Keep in mind, the double bond was broken, double to single bond. Once our product was alcohol, in the other reaction, our product was a halocarbon. Now I'm going to give you 1 minute to read page 805 of your textbook, and I need you to identify some main points. Please go through it. I'm going to read it with you to make it a bit easier. How are addition reactions used in organic chemistry? The carbon-carbon single bond in alkanes are not easy to break. In an alkene, however, one bond in the double bond is somewhat weaker. This bond is easier to break than carbon-carbon single bonds. So it is sometimes possible for a compound with the general structure XY to add to a double bond. In addition reactions, a substance is added at the double or triple bond of an alkene or an alkyne. Addition reactions are an important method of introducing new functional groups. They're an important method of introducing new functional groups to organic molecules. They are also used to convert alkenes to alkanes. In general, the addition reaction shown below, XY, represents two parts of the reagent that are added to alkenes. Okay, so let's see what we got. Main points after reading. First of all, alkanes cannot undergo addition reactions. RXN means reaction, so keep that in mind, okay? Why? Because they already have stability. They already have a strong, stable structure. So we agreed alkanes cannot undergo addition reactions because they already have a strong, stable structure. But who can undergo addition reactions? Mainly double bonds of alkenes and triple bonds of alkynes. Why? Simply because the double bond in double bonds, one bond is weaker. And because it is weaker, we can easily break it. Okay, so this is what we have so far. And the third point we got from reading the paragraph is the definition of an addition reaction. Remember, reaction are Xn, which is when? What is an addition reaction? When a substance is added to a double or triple bond alkene or alkyne. We are going to see why and how we do this now. So, we got our important points. Carbon-carbon single bonds in alkenes are not easy to break. In alkanes, however, one of the bonds is somewhat weaker, which is why we can simply easily break it. What is an addition reaction? It's when a substance is added at a double or triple bond of an alkene or an alkyne. This is generally how an addition reaction looks like. Our reagent is XY. We are going to see what are our XYs. Now, how are addition reactions used in organic chemistry? We discussed it when we read the paragraph. You have 45 seconds to try to get the answer and write it down. How are addition reactions used in organic chemistry? Or what's the importance of using addition reactions? Are you done yet? Okay, time is up. So let's see how are addition reactions used in organic chemistry. Simply two things. First of all, it's an important way of introducing new functional groups to organic molecules. We're adding functional groups to organic molecules. Also, to convert alkenes to alkanes, because we can clearly see the double bond in alkenes is broken to have a single bonded alkane. Now, keep in mind the questions with copy into notes need to go into your copybook. And also, keep in mind the general formula. The general formula is plus yx gives me and my y and x are here. This is the general formula. Now, the second question is, define an addition reaction. I need you to define what an addition reaction is and copy it into your notes. We already discussed what an addition reaction is, right? So we can easily define it in our copybook. Okay, so time is almost up. Let's define an addition reaction. An addition reaction, it's simply a reaction where a substance or substituent, let's say, substituent is added to what? To a double bond alkene or a triple bond alkyne. Simply for two reasons. First of all, to introduce new functional groups to organic molecules and to convert alkenes to alkynes. Alkenes to alkanes. Now, why can't alkanes undergo addition reactions? This is our last question before we actually go into talking about all the types of addition reactions. This question is pretty easy, so 30 seconds are enough. Why can't alkanes undergo addition reactions? It's one simple reason. Why do you think? Think of the reasons we use addition reactions. There's a reason that helps me find my answer. Okay, so time is up. Simply one simple answer. Alkanes already have a single bond. Remember when we said we use addition reactions to convert alkenes to alkanes? Already we have alkanes, so they're already very strong and stable. But alkanes can only swap in substitution reactions, like the substitution reactions we took in previous weeks. Now, let's start with the first kind of addition reaction. What I need you to do is analyze the product of this reaction. Take a look at the product and try to deduce what is a hydration reaction. What can we notice in this reaction? What do you think? Take a look. Well, first of all, we added water, H2O. So, in a hydration reaction, we add water. How about the result or the product? The product in an addition reaction is an alcohol. So, a product is an alcohol. When our product is an alcohol, so due to this hydration reaction of adding H2O, we get a product, which is alcohol, because ethanol is an alcohol. And of course, our double bond is reduced to a single bond. So simply what happened is they deleted one bond from here and they added one here. So here we have H and here we have OH. This is simply the hydration reaction. Talking about words in hydration reactions, A hydration reaction is the addition of water to an alkene. Keep in mind alkene that is reduced to an alkane by breaking the double bond, and we add water to get a product that is alcohol. So always take a look at what we add and what the product is. A hydration reaction results in the formation of alcohol. For example, this is the example that we just took. It's a typical hydration reaction. Addition of water to ethene, we get ethanol, the alcohol. Now, I need you to predict the product of the hydration of propene. Suppose that you ran an experiment in which you performed a hydration reaction with propene. What would you expect the product of this reaction to be? So they want us to find the product. Remember the two things that we do. Okay, we added water. What next? What should we do? I'm going to give you a 30-second timer, and let's hope you get it clearly and easily. What is the product of this reaction? We have propene, and because it's a hydration reaction, so we add water. What is our product though? Remember the two things that you should do. First of all, break the double bond. The second step is to add the water to get our product, which is the product in all hydration reactions is an alcohol. So what we get, keep the carbons as they are. Carbon, carbon, carbon. Keep in mind, we broke this was a double bond. We have one now. The hydrogens are here. So this is our product. We simply get this hydrogen and this OH. We open the double bond and simply add them. This way we got our product, propanol. Now, what I need you to do is take a look at our second addition reaction, the halogenation reaction. From its name, halogenation, so we add a halogen. Okay, so in halogenation we have two kinds of products, a di-substituted halocarbon and a mono-substituted halocarbon. So what's the difference between mono-substituted and di-substituted halocarbons? I need you to observe this picture and try to conclude the difference. How are they the same? How are they different? The timer started, so please take a look at both and try and think what is the difference between mono-substituted and di-substituted. From their names, try remembering from their names, mono and di. Think about it. Okay, so time is up. Let's put 1 point in mind to actually make everything easier. Mono equals 1, di equals 2. And substituted means we add something. Okay, so di is a prefix for 2, so 2 halogens are substituted because we said halogenation reaction, so a halogen is added. So this reaction is di-substituted. Why is it di-substituted? Because we added 2 halogens. And a mono-substituted reaction, remember, mono is a prefix for 1, so 1 halogen is substituted. This way, we can add hydrogen halides. We can add this hydrogen, HX, hydrogen halides, or halocarbons, let's say. So in mono-substituted, we add one halogen. Di-substituted, we add two halogens. So, like we said, mono-substituted is where one substituent is present in the product. Di-substituted, two halogens are present in the product. Now, take a look. Let's put it into actual words. We agreed the general formula for an addition reaction, the other reactant is XY. In this way, it's a halogen molecule. So it can be F, I, be bromine, iodine, fluorine, chlorine, halogens. The product of the reaction is either di-substituted or mono-substituted. In this example, we have ethene and bromine. So 2Br di-substituted because two halogen groups. What we do is immediately break the double bond. So we have here, and what do we have? Hydrogen, hydrogen, hydrogen. We have the Br1 here, and the other is here, and the rest are hydrogen. So what we did is we opened one bond and added the Br. This is a di-substituted halogen. Another example is the mono-substituted, because only one substituent. It's like hydrogen halides. We have the hydrogen and the halogen, hydrogen and the halogen. We can also add them to double bonds to break them. We have ethene, for example, and hydrogen chloride. So what we can simply do is break this bond, add a Cl here and an H here. This way, this is the product we get, a chloroethane, which is simply a halogen. Our product in halogenation reactions is a halogen. Now, I'm going to give you 30 seconds to compare between mono-substituted and di-substituted halocarbons. Please take your time, focus, write them on your copybook. We already discussed the difference, right? Okay, so time is up. Let's easily compare. Like we discussed, mono substituted, mono equals 1, so one substituent only. For example, HBr, HCl, HF, and di-substituted, di is a prefix for two, so two substituents. For example, I2, F2, Br2. So simply be careful with halogenation reactions because we only use halogens as substituents. Halogenation, only use halogens. Okay? Of course, copy all these questions into your notes. Now, I'm going to give you 30 seconds to predict the product of this halogenation reaction. What do you think the product is? This 2Cl, so it's di-substituted, right? What would the product be? What do you think? Did you get it yet? Okay. Simply check your answers with me. First, we break the double bonds. So we have carbon, carbon. We have 4 hydrogens, 1, 2, 3, 4. And we have 2 chlorine. Because we broke a bond, we need to put them in the places of the broken bond. Perfect. Now, the last kind of addition reaction is the hydrogenation reaction. The hydrogenation reaction, from its name, the addition of hydrogen to a carbon-carbon double bond. When we break these bonds, we add an alkane, we produce an alkane, because we agreed in all addition reactions, we are simply deducing from alkene or alkyne, let's stick to alkene, to alkane. We are deducing. So what we have is, we break this double bond and we add hydrogen because it is a hydrogenation reaction. What happens is, we broke the bond, so we have a single bond, and then we add the hydrogens. What I need you to do is try and predict the product of this hydrogenation reaction. It might seem tricky, but it's really one of the easiest. So take a look and think about it. What do you think? Did you get it yet? Okay, so time is up. Let's see. What we have, the double bond was here, right? So what we should break is the bond here. So we have 2 hydrogens, 2 hydrogens, 2 hydrogens, 2 hydrogens. Here we used to have 1, right? But we broke the bond, now we have 2. So we added a hydrogen in the place of all the double bond that we broke. I hope this example of a cyclohexene was clear. We can notice here that PT is used as a catalyst. Keep this information in mind. Hydrogenation needs catalyst. Okay. Finally, I'm going to give you 30 seconds to try and compare hydration and hydrogenation reactions. Okay, so there's 1 minute for you to compare hydrogenation and hydration reactions. This way, we fulfilled our first objectives, describe how addition reactions are used in organic chemistry. We agreed to introduce new functional groups to organic compounds and to deduce alkenes to alkanes, apply understanding of the 3 types of addition reactions. We took examples, we discussed hydration, hydrogenation and halogenation, and now we are comparing hydration and hydrogenation. Did you get it yet? Okay, so let's check our answers. First of all, both are addition reactions. This is how they're similar, right? Both are addition reactions. Now, how are they different? Let's take a look at the products and what we add. Hydration addition of water. And what do we get? The product is alcohol. For hydrogenation, the addition of hydrogen. And what is our product, or what do we form? Formation of alkanes. Let's also put the points for halogenation reactions. So, halogenation, addition of halogen, and the product is a halocarbon. Are we clear? Is everything clear? Please, I'm waiting for your questions in the first live session. You're supposed to watch this recorded lesson before the second live session. I hope everything was clear, and see you next class, inshallah.